You could step in if we need to, but I don't know. He's the beginning stuff, right? So if maybe you want to present that, and then he can present stuff later, or step in to answer questions.
Okay, we're probably going to get started, and I'll present this at the beginning.
Do you want me to stay up here while you present?
Sorry, the system's presenting right after, so makes sense. Should we go ahead and go for it, or?
Yeah, let's get started.
Alrighty, we're going to go ahead and get started. Well, change over some methods, but we're going to go ahead and get started. So quickly, welcome obviously to preliminary design review. It's been a minute getting here, but we are here. So to go over quickly the agenda. So we'll start out with just kind of going over a high-level robot overview, show the full robot TLA CAD, discuss a little bit about the competition to make sure we're all on the same page there, and for those of you who are not in the robotics, understand what our objectives are. Then systems will present on kind of our overall concept of operations, our technical performance measures, and how we are currently stacking up to those. Then XStep will present, then followed by Drivetrain, with time for question at the end of each of those presentations. We'll break for lunch, and software and QH will present, and then we'll finish up by discussing a little bit about what is expected at CDR and what kind of our plans moving forward are. So, to jump right into it, to quickly go over what our objective is. So this is the picture of the NASA Lunobotics competition arena in CAD. You can see that we have a random distribution of the lighter red is boulders, and the darker red are craters. So those will be randomly distributed. The quantity will be roughly these about 4 boulders, 3 craters in the excavation zone, and 3 boulders and 1 crater in the obstacle zone, and then in the excavation zone. But the placement will be random. The small lines you can see in there is what we will be attempting to make or dig. Those are our trenches. They're approximately, we're shooting for about 1 meter long, and depending on some various factors, we expect to be able to make 5 to 7 trenches per run. So you can see there is going to be some difficulties with placing those trenches in the excavation zone. But this is what the overall arena looks like. And our goal is, of course, to start from the starting zone, and we will navigate to the excavation zone, trench, then store that material, move it to the berm area, and deposit it. But now looking at what our current design looks like. So of course we'll go into more details in later presentation, but here's the overall TLA. So our excavation system is a bucket elevator trencher system. So basically that will spin backwards as you see it here, collect material, push it into our deposition system, which you can see modeled by the auger in the middle there, and it will come out the rear of the robot. Our PH box is mounted vertically on top of the robot instead of previous designs where we put it sideways. This was for ease of access and to allow us to actually put a hinge and latch system on the PH box, so therefore there will be no screws and the lid will be easily be able to be opened and we can do any maintenance we need on the PH box. Additionally, so we are defining the forward direction as the excavation system. This would be the forward direction of the robot. To comply with NASA rules, we'll have 4 hoist points. These will be connected via cable to a central cable. That will enable the robot to be lifted via crane. We will also have lift points located below the frame at these same points. And lastly, to get some nomenclature out of the way, the robot has 3 configurations. First being storage. This is when the excavation system is roughly lowered to be equal with the wheels. This is to maintain our maximum height during our actual inspection. Then traversal configuration, that's just moving the excavation system up to allow us to avoid bottom out height and not hit any obstacles. And then of course our trenching configuration, this is when the system is lowered about 3 inches into the ground and we're actually able to dig. And I'll hand it off to systems.
All right. Real quick, systems members, if you would like to come up, the ones that I've said to present, please do. Before we get started, for everyone that is presenting, something that is a little bit new this time around is that we do have a mic, and I am recording this PDR session. So when you talk, please stand around the mic if possible. That way it can pick up your audio. Of course, if you have to answer questions and go around, that's perfectly fine. We are also taking notes on the questions themselves, but when you present, please stay around this front area for us.
Okay, so one of our deliverables we need to prepare for NASA is our concept of operations, which describes how the team operates the robot system elements in terms of all the hierarchies of our full robot system and keeping in mind the environmental conditions of the competition in order to accomplish the mission. So,
all right, so the concept of operations is primarily broken down into 3 sections. The first one is objectives, which you'll see on the next slide. Second part is operations requirements, so basically what do we need in order for the robot to operate? We need a robot that can operate safely, like no maiming people, reliably, we don't want it to break down in the middle of a run, and efficiently, we don't want it to take a really long time doing something and then not be able to continue doing that. And then the third part is environmental constraints, so dust mitigation. Too much dust in the robot is not going to be helpful for the robot. And then obstacle navigation so it doesn't get stuck during a run. All 3 of these together are kind of what fits the concept of operations. Objectives?
yes, so the objectives, that was the first part. Basically, the things we covered earlier in terms of the goals of the competition: efficiently traverse the terrain, construct a berm while avoiding obstacles, and operate without posing any hazard to people around it. Okay, so this is our operations process that we have designed to take into account all the requirements while meeting the objectives. So we have our startup phase where we ensure the robot is ready to go. We wait 20 seconds and establish the remote connection. This is all covered under the startup phase, so it doesn't eat into our time for digging. Then we move to the starting ascent phase where we extend our linear actuators, and if the current on those stalls, we go to our safe phase which will go to the safe phase at many points. If any of the motors are stalling in the safe phase, we cut the motor power and enable manual control. But if the motor current is nominal, we're going to continue to the initial mapping phase, where we will get an initial view of the field and then set our target to the excavation zone. From there, we can move on to selecting a location for excavating, traversing to that location, plunging to dig, trenching to collect material, bringing it back up, traversing to where we want to deposit it, and then depositing it. And at any point, if the match time expires or the e-stop is pressed, we enter shutdown mode and turn off the robot and display the power usage. Anything else in that?
All right, so this is a visualization of how our operations will go. So it will start, the robot will start in the starting configuration. That is the box down there, the one that has the dashed green lines. It'll be in a random configuration, and the robot will rotate itself 360 degrees to serve the arena and find the April tag. The April tag is what will establish the absolute position for the robot, so it knows where it is in the arena at all times. From there, the optimal path will be chosen by the path planner, so robot will turn around, survey the arena, establish itself as where its front is, find its location that it wants to go to, and then find a path that is optimal. So for the excavation and deposition cycles, we estimate that there will be about 5 to 7 excavation and deposition cycles for a 30-minute run. The material deposited from with the robot is about 0.25, so a quarter meters into the berm area. It'll dig into that, and then the deposition location will be shifted over because of the possibility of the wheel sinking into the trench that was already created. This is so that we can continue digging in a relatively compact area, and new excavation location will be determined each cycle. So one cycle of the excavation will happen, go deposit into the deposition, and then once that happens, it'll go back to a new location and then continue that cycle again. So here are our current TPM statuses. TPM stands for Technical Performance Measures. These are the quantities that we want to keep track of to make sure our robot is designed in a way so that we won't exceed any of our thresholds for the competition. Over here, the TPMs, we have units such as mass, power, bandwidth usage, all the geometrical constraints. We have capacity for regolith to be stored and the build period. This is to make sure that we're depositing enough and building enough during the competition, and power, instantaneous power usage. The thresholds are there, and the bounds establish whether this is an upper bound or a lower bound for that threshold. It has the system requirements that it is derived from, and the subsystem rollup is what the current the current TPM distribution is from all the subsystems stacked up. Here on the left, on the right, we have the first estimate of our TPMs as of right now. So this is where we currently stand with our TPMs. With our requirements, there are several requirements that we have identified going into PDR as at risk. This may have changed because of the fast-moving pace that we've gone with the PDR. However, this is what we've identified going into it. So the first one is the requirement 311. This is that the probable failure of components that are probable to fail need to have spares or are quickly procurable and easily manufacturable. This one was relatively new, established after the original design review, and so this one, not all subteams may have been aware or have enough time to look for this, but this is one that we need to make sure that all our components that are at risk of failing have either spares that we can swap out during competition or are procurable overnight or makeable during competition. The second requirement is 6.2. This is to aim for bandwidth of 10 kilobits per second per kilogram of robot mass. So the upper threshold we have is 5 megabits per second, but NASA says that we should aim for this value here. And so we have yet to calculate if that is what we're at right now, but this is one that we could exceed with our rough estimates of our bandwidth usage. And lastly, we have system requirement 923. This is to make sure that the robot safes itself within 3 seconds of disconnecting from the robot operator. So if it doesn't receive any input from the operator, then it'll shut itself down because it we have no idea what the robot is doing. And so this one was overlooked during our algorithm design and making sure that was part of it. So this is what we will make sure, these are the requirements that we'll make sure that we address going into and preparing for CDR. This list may change during PDR. We may discover new requirements that are at risk, or we may find that some of these have already been addressed in some way.
Does anyone have any questions right after that for systems or anything about ConOps or TPMs? Yeah.
Could you point where April is on the map?
The April tag?
Yeah.
So the April tag would be, so basically we're allowed to put anything around the berm. So the idea would be to put the April tag on this right side of the berm area. That way, when it does its starting configuration spin, so basically the robot's going to spin 360 degrees, that the camera would see it. And that would, mainly the objective there is to establish orientation within the arena, because we have to relate our relative orientation within our map of point cloud map, and then our absolute relative orientation with respect to the arena. We also will have ultra-wideband sensors, which software will get into, to try to establish that where the berm location is distance-wise. Any other questions? Yeah.
For the systems, what is the RPM number that is like the critical value to be under? For the risk?
Oh yeah. So for that, that was briefly went over, but the actual value we're looking for the at-risk. That one is in the DFMIA that we did. If the probability, so the occurrence is at a 7 or higher, then that would be considered probable failure. And so any components that you analyze or systems that you look at, subsystems that have a probable failure of at least 7 or higher, we'll need to look at and see if you can have spares available for it during competition, procurable overnight at the competition, or makeable at the competition using the resources that they provide.
Okay. Do you have the cumulative number, like the multiplication of the different risk factors? Like 120 RPM, whatever, or like something like that.
That was going into CDR for all of the failure modes that we looked at. If the RPM value was, if the RPM value is over 100, we'd like to have you have some sort of plan to try to mitigate that. If it's over 250, we cannot go into CDR with that. So it needs to be below 250 by the time CDR comes around. Yeah.
Awesome. Thank you very much, Max. Okay, so to kind of, I'll briefly kind of touch on what we've kind of done some rough calculations to try to calculate what our expected score will be at the NASA, both NASA and the UCF competition. So to quickly kind of go through the assumptions that were made here. So driving data was largely based on previous EOS performance and basically looking at the video recordings and mapping a expected speed based on, assuming that we are avoiding obstacles and basically taking average speed, which was calculated to be about 8 centimeters per second. And then from that, we basically estimated a trenching speed to be about 2 centimeters per second based on expected forces and more or less an engineering educated guess. From that and the motor characteristics, the expected times for trenching, for depositing, for traversal can all be calculated, and therefore we can establish how many excavation cycles we think we can get in a 30-minute and a 15-minute run. So at the Kennedy Space Center competition, we expect to be able to get 5 to 7 mining cycles, and the UCF competition we expect to get 2 to 3 cycles. And the uncertainty there is related to traversal times, both initially. You can see our range for travel to the excavation site expected to be within 2.7 minutes to 5 minutes, and some uncertainty with traversal during transition between excavating and depositing, which we have about a 1.5 minute buffer as an extra additional time based on our calculations. So to jump into the scoring breakdown, I'm going to take it category by category and look at how we currently stand. So first point is passing communication check. That gets us 1,000 points. That's basically robot works. For mass, for every kilogram of robot mass, we lose 8 points. So at our current mass of 42 kilograms, we're losing 336 points there. As well as for every situation camel use, we lose 4 points per camera. So right now we're assuming we would use 2 of those cameras to basically be able to watch our robot in real time. Moving over to kind of the construction category. So berm construction, based on a 30-minute runtime, we expect to be able to collect about 52 liters of material. That's assuming we achieve 6 cycles, so taking that average. That gives us 130 construction points. Average data bandwidth, this is basically on that target of 10 kilobytes per second. This could change, but that's minus 8 points. And then energy consumed. So based on those motor run times, based on those previous estimates I talked about, we assume to consume about 48.25 watt hours per competition run. So that's why we would lose about 48 points there, as we lose a point per watt hour. Looking at UCF, this will be the only thing that changes between the competitions. The points per liter of berm is doubled, but of course we're going to collect a lot less because the timing is a lot less. So only 85 construction points for the UCF competition. Looking at the next category is dust tolerance. There's a maximum of 100 points scored here. Based on our current designs, this is just a basically, frankly, my opinion on what we could expect the judges to score us for. So enclosed drivetrain components, that is something I believe we achieve. And digging without dusting up crushed basalt. Due to us mining in reverse, we should see significantly less dust projection. But as you can see, there's significant points to be gained in this category, as we're looking at only achieving 80 construction points for building a berm, but we have 60 more to gain here on just dust tolerance. And lastly, the last point category is autonomy. Our goal, of course, is full autonomy at 500 points, and this would be full 30-minute run, 0 manual input into the robot, other than start. But kind of our more short-term goals would be to achieve dump or excavation autonomy, as well as traversal autonomy. So that would put an estimate about 250 points. So kind of what that all adds up to is scoring about 1,000 points in either competition. You can see the point breakdown here where based on this score and our placement, we would get 25, 20, or 15 points respectively for first, second, and third. If we do not place in the top 3, we would get 1 point per 13 liters of construction at the KSC competition, and for some reason that's changed by order of magnitude at UCF. I'm not exactly sure why, but that would basically be able to do our placement in the top 10 to qualify us for the NASA Kennedy Space Center competition. All right, does anyone have any questions about the scoring or anything regarding that? Otherwise, we'll move into XStep. Yeah?
Were the autonomy points additive? Like, if you get like 1 cycle, you also get driving?
So, if you get the full autonomy cycle, you cannot score for excavation, dump, or traversal. So, the max is 500 points. Yeah, so you don't score for the previous if you can get the next high up. Yep.
What's defined as a cycle? This is full autonomy from
So a full autonomy for the one cycle is defined as a full traversal, excavation, and deposition cycle. I do not believe you have to actually traverse. Well, I take it back. You have to traverse from the starting area initially, and then do the whole cycle. So it does have to start from the starting area.
So essentially, like if you somehow the autonomy messes up, like from the start of the run, but you get to the construction zone and for some reason it's able to kick back in, you won't get the one cycle.
Correct. Yes. Yeah, it has to start from the starting area. Well, it would be we would have the ability to establish localization manually and set targets manually. Yeah, Mike. Okay. Mike, did you have a question or no? You have a question?
Did you do a trade-off study on like how many points you think a skilled operator gets compared to the points you get from full autonomy?
We have not. I think that's largely based on traversal times, which is kind of the biggest uncertainty in this analysis, as I really just don't know how. I guess it's how fast can the robot go with autonomy versus how fast can you go with manual. Presumably you can go much faster with manual control, but that might be something we should look into at CDR. Yeah, that's a very good point, yes. But obviously this is going to be dependent on a lot of testing next semester on how well we can get autonomy to work. All right. Any other questions? Move in next step? All right, awesome. Next step, any questions?
Okay, we are next step, but we're starting off with an analysis of continuous mining versus single action mining systems, which I'll let our president take away because I didn't do these slides.
Yeah, so basically to give some context here, at our last design review, we were evaluating between a trenching system or what we're calling a big scoop mechanism, basically a single action mining system without a deposition system. So from that, over the last couple of weeks, we've basically sought to try to see how bad the cons of a single action mining system are. So less theoretical model, but most importantly, what is the torque requirements and the reaction forces for a system like you see on the right, which is basically a giant scoop, and are those enough for the trade-off of simplicity for a single action system not to be worth it? So we made two prototypes. You can see the V1 and it should be labeled V2 on the left there. Basically, the first prototype, although it worked, was too big and required too much torque to actually mine into the ground. So we shrunk the system in half, as well as cut the trailing edge, as that increased the amount of torque that we needed as that rubbed against the ground, to be able to get a full characterization of what torque would be expected on this type of system. So you can see the expected volume, even with a 3.5-inch cut, is only about 3 liters and the biggest in the V1 prototype. So not a lot of volume capable of being collected. But if we drove forward or had some sort of other mechanism pushing material in, that could be increased theoretically. So to start the analysis, we first looked at a purely mathematical analysis on the force required for mining. So this was based on what's known as a Zhang model. Basically, there's 3 forces at play. the frictional force on the back side of the blade, which due to the blade in a circular fashion moving away from the soil, that's going to be roughly negligible. You also have the passive earth pressure, so that's kind of like the pressure force of the soil, basically pushing on the side of our bucket. And then you have the side friction force, which is the friction between the blade and the soil, as well as the force to overcome and basically fail the soil. And that's going to be an order of magnitude higher than the passive earth pressure. The passive earth pressure. So based on these results and the V2 prototype, a relationship can be driven between depth of cut and torque required at a max angle of about 85 degrees as our rake angle. So what the degree of the blade with respect to the ground. Which you can see it gets very high as we go into reasonable depth of cut to get sufficient volume. To validate those results, we made an experimental test setup, as you see here. Basically, the scoop mounted to a shaft with a torque wrench, so we can measure the torque at each depth of cut, as well as putting 20 kilograms of regolith on each side to basically simulate the mass of the robot. From this, and the V2 prototype, like I said, the V1, we were only able to dig the 1.5 inch cut, but for the V2, we were able to go all the way up. That should be 2.5 and then 3.5. And you can see from the, at a 1.5 inch depth of cut, which is about half a liter, we're seeing 15 newton meters, and that's jumping up all the way to 81 newton meters, 70 newton meters at a 3.5 inch, which is still only 1.5 liters of volume collected. And you can see this air related to the model. So the model is not exactly perfect, and the paper even states that. But this is our kind of our relative air, maximum being 50% air, but we're seeing 15% air at 2 of those data points. Of course, we do not have a lot of data points, so it's hard to really get a full comparison of the data. So lastly, to kind of wrap that up, single action mining systems simply just require too much torque, and that is why we pursue continuous mining. That model basically that I showed can be used to reasonably calculate estimated torques, but for our current system, it predicts a torque of only 1 newton meter, which based on last year's data is significantly less than what we might expect, and that is because the operation of digging via plunging and trenching is significantly different that the model cannot account for. Yeah.
Okay, hitting it off with our actual systems overview. So our last year's system was about 17 kilograms in the CAD model with all the fasteners and everything included, including like dust covers and pretty much everything except like the lead screw dust cover and some of that 3D printed components. Right now, our current model, including the actuation and excavation like assembly rolled into one, is 13 kilograms, but we don't have all the fasteners and dust covers and we're missing the chain. So that'll probably increase to about 14, but there are definitely some weight savings we can do on top of what we already have to further optimize the system and really gain back some points from that mass of the robot. Some of the important changes to our system from last year and kind of what we've designed this year are the overall structure of the robot, or for excavation, how it's tensioned, how the scrape plate works and how it interacts with the system, and then also the bucket design and the linear actuators for how we actually move it up and down into the ground or for traversal position. Starting off with the structure, instead of having 2 struct rods and a lead screw to power the system, we now just have 3 struct rods. We have a top plate and a bottom plate where if you look at that bottom image, you can see the struct rods are going to be tapped at the end where they're able to fit into the plate so that we have a well-defined length of the overall system that will not shift and the rods can't be basically push through the plate entirely and cause it to slip and lose tension. So overall, there's 3 machine struck rods, 3 linear bearings in the center on that structure plate. We have 6 rod clamps, 3 on top, 3 on bottom, and single plate holding the linear bearings and the whole system up. And then also 3 plates, 2 at the bottom, 1 on the top. And that allows for the tensioner system. Moving on to the tensioner system, to kind of reduce some of the complexities of having the tensioner on the top sort of structure system for the drum, instead of moving the drum, we're going to be moving, or instead of just moving the drum and not like the motor, so that we have to deal with the larger tension for the actual like chain driving excavation. We have this sort of pancake design where basically that bottom plate that's a bit smaller with the 2 screws and the struck rods going directly into it, that's going to be a fixed position from the top, but the plate on top of it is actually what's supporting the bottom drum of excavation. And as you tighten those screws, it will lower down, causing the top and bottom drum to become farther away, tensioning the system. So once you screw those into the desired tension, then you will clamp down this 3 struck rod clamps, and that will be able to hold the majority of the tension, also with the actual like screws tensioning the system. And the goal with this is to have it be a little bit easier and kind of reduce the complexity of the top tensioning system for the chain driving the whole system, and just make it easier to manufacture, ideally. As for buckets, we're going to have a lot of really simple buckets. That's pretty much what they look like. It's an L channel with 2 L channels on the side. Right now, it's about 6 screws or fasteners per bucket, and they're all very simple. It's just 1-inch L channel with like squared off in the center, and then 2 on the side, which are 1x1s as well. It's very simple, but potential changes in the future, depending on what the scrape plate and stuff looks like in the end. As for the scrape plate, right now, we're able to trench about 3 inches deep into the ground, but that's not accounting for wheel sinkage or the grousers. So that could be as high as 3.5 or even 4 inches, depending on those factors. Also, as you can see, the buckets are, of course, going down over the front and then back up, scraping against that plate. The scrape plate is also integrated into the bottom drum structure, so you can kind of see what's highlighted there. The whole channel going up and holding that actual like 16th inch scrape plate is part of that same bottom structure side plate. Also at the top, if you look at the left image, we have a slot because for the tensioning system to actually work, we have to have the 2 top and bottom structures not be rigidly attached. They have to be able to have some give, so we have a slot built into the top plate of the robot. As for how we're actually moving this whole system up and down, we have 2 linear actuators, 8-inch stroke. It's like 1.2 inches per second. So going from the maximum to the minimum is 8 inches. It should take about 6 to 8 seconds under load. So switching between driving and mining or trenching position should not take a lot of time. These are connected to the top structure just via bolt and like pin, sort of similar to what we had on the wing plates of excavation last year. And the bottom side, right now, it's basically there's just a cutout for that sort of squared off fixture at the bottom of the linear actuators, and that will go straight through the structure plate holding up the whole system, and then we're just going to put a bolt through it, pin it, because it won't be able to move laterally at all compared to that plate, and it will be pressing down on that plate, so it's really just to prevent it from just straight up falling off of the actual system. But all the weight should be pressing down on it pretty much at all times, so hopefully the stresses are not going to be very high on that. We'll do some FEA on a lot of parts of the system to further optimize it, but that's kind of a general overview of excavation.
brings us to the deposition system, which for this year has been completely redesigned from the previous year. It is now using, it's a largely stationary system that just has a 2-foot, 4-inch diameter auger running through that middle. The auger is comprised of two 1-foot plastic flightings that will be fitted onto a 1-inch hex shaft, which will run through the entire piece. And then the bottom tube of it is just a 4-inch PVC pipe, which has an inner diameter of slightly larger than 4 inches, which will work out for us. And then the walls, the sort of big walls of the bin, are just made from 1/16 of an inch aluminum sheet metal, and then the actual structure of the system is comprised of 1/4-inch aluminum plate, which are these ribs that you can see on the front, middle, and back. These are then connected in a way that I'll describe later. The system is using the Crozet motor, which is the motor that we used for actuation last year. The deposition motor has been found to be insufficient for our purposes, and so we've switched to a different motor. We're going to be using a 100-to-1 gear reduction on that to get it down to the RPM and torque that we're needing. The system is right now looking at about 5.5 kilograms. That's of course expected to go up once we put in fasteners and a couple of other bits and bobs that are not currently pictured. And it's expected to have a 10-liter capacity total, which is much higher than the big scoop capacity that was noted earlier. Looking at the structure, the entire thing is basically held together by a bunch of 1x1 L channels. We don't have 1x1 L channels in the model right now due to some difficulties with the PDM system, which will be overcome after PDR, but they're going to be switched out to 1x1 L channels. They'll be either riveted or tack welded to connect those L channels to the 1/16 of an inch walls, just because those are mostly aren't particularly important. We'll be using actual bolting to connect them to the 1/4-inch side panels, which you can see in the middle. You can see right above the round tube bottom, there is a side panel. There's a side panel right here. Those are 1/4-inch, and so those are going to be very important structural pieces. And then on the front and back, we have two 2x2 L channels, which will serve as the connection point of the deposition system to the frame. Talking now about the mounting, at the back, the deposition system is connected to the frame with 3 strap hinges. This is because for the load cells, the system has to be able to bend to move around at least a little bit. Speaking of which, the front of the system is mounted on 2 load cells, which it's not pictured in the CAD again because of PDM issues, but it's going to be resting on 2 20-kilogram load cells. Probably we'll just have some screws, some bolts running up through the front holes of the back holes, of the load cells, which then that 2x2 L channel will be resting on to be able to create the necessary flexion in those load cells to measure the weight of that we need. The load cells right now, it looks like they're just mounted flat on the frame. That's not correct. They'll be offset by a spacer because they have to be able to bend in the middle, and so being mounted straight on the frame doesn't allow for that. And talking about the motor, we're going to be running at 51 RPM for standard operation is what we're expected. The motor outputs about 3,400 RPM, and so we're doing some gearing to get that down to the range we need. That says 99 Newton meters. That's incorrect. It's supposed to be, one second. It is definitely 19 Newton meters of torque. I know everyone got excited and thought we were about a sheer god there. Nope, just 19 Newton meters of torque. It's running at 24 volts with 5.4 amps of current, and it's nominal running. And then we're going to be using a sprocket and a chain to connect the motor to the shaft, the auger shaft, which again isn't pictured. And then we're going to be using an idler sprocket as a tensioner to keep that chain in the correct place, which also hasn't been pictured, but that system will probably just be a bolt sticking out in a slot with a screw and then an idler tensioner on it and then another screw to hold it on. It'll be quite simple. And then we, of course, ran a DFMEA looking at the deposition system. We looked at 3 components to be considered for failure. The motor bracket, which is that whole front plate that has the motor and is also connected to the front of the and then we looked at that bracket's connection to the bin itself, and then we looked at the motor belt or the motor chain, and whether that will, and so the biggest risk that we identified is the motor chain falling off / breaking during competition run, which is of course a real possibility. We encountered some problems with chain messing up and breaking and being torqued last year, and so that was by far the biggest risk. The way we intend to account for this is through extensive testing and also really looking at that tensioner assembly and making sure that it is sufficient to keep the chain in place while not putting too much tension on the chain in order to prevent any sort of bending. All right. Is there any questions? Yeah, Josh.
All right. First, I have a question for excavation.
Yes.
If you one more slide, I think. Yeah. Okay. So, when the excavation system is at its maximum height,
Yes.
what I see worried there is, and I saw it in a picture in Nate's first presentation, it looks like the center of mass of that system is going to be pretty high above its pivot point while it's traveling, which means that if your wheel hits a divot and the robot pitches down suddenly, that's going to cause some pretty big flexing on that part of the system. So I just want to know if you guys have accounted for that, or
Not a huge, a lot of analysis yet, but what? Okay. We did a while back. It was really high vacuum safety, but that doesn't necessarily account for the dynamic forces of it all and the momentum of the system. We are going to be doing more FEA to just verify that this is good, but with the sort of tripod design we have and it being 3 actual strut rods instead of slightly less stiff linear actuator or lead screw from last year, I don't necessarily think the forces will be extreme, I guess, but it's definitely something that we do need to keep aware of and design for moving forward. With the system being so much shorter than last year, last year it was horizontal most of the time, and any amount of sort of drivetrain shock would still be transferred to it a little bit. It's just that moment was such a big distance, and it was really just vertical forces. If we ever went into a crater or hit something and jolted upward or downward, a lot of that would be transferred to the system because of that long moment of the system. So shortening the system overall and increasing the strut rod sort of configuration and adding another, I think that will overall improve it. But yeah, we still need to just verify that analytically.
yeah, I would just do some FEA analysis where you essentially apply a large torque on that pivot point, where the pivot point is trying to rotate relative to the rest of the system just to see how it responds.
Yeah.
My second question was for deposition. Can you go back right there? So those corner and side panels you have,
Yeah.
are those mounted directly to the PVC tube?
No, the PVC tube is actually sort of just resting in the ribs. It does slot into the front and back plates, but the PVC tube isn't really structural in a sense. It's really just there to support the regolith. And so basically the PVC tube just lays on the ribs and will slot in at the ends, and then the quarter inch side panels are really what's taking the load.
All right, and the side panels are attached directly to the ribs and nothing
Yes,
else?
directly to the ribs and directly to the front and back. It also not pictured, but it's also going to slot into the front and back plates just for a little bit extra security.
Again, due to PDM issues.
PDM issues.
Yeah.
It's supposed to look like a smiley face.
Yeah, basically these, okay, you can kind of see this previous plate on the bottom half, like that slot, so you know, like with that sort of precise laser cutting, like we'll be able to do that pretty accurately, and there will be like a slot here and here, so it really looks like a happy.
It looks like a
happy
smiley
little dot.
face.
But yeah, also a lot of this system and also excavation are 1/4 inch plate right now. Totally overkill for a lot of things probably. So yeah, we'll definitely be optimizing it better than it is now for weight. But like 1/4 inch plate is 1/4 inch plate. It's very strong, so a lot of it will be a lot more rigid than it necessarily needs to be.
Yeah.
But yeah.
Yeah, you could probably knock that down to 8 and 3/16.
Yeah.
So, other than that, I think I'm good. So,
Brian, I know you've had anything.
Yeah, so for the, is that with one part? Is it kind of bad?
No. So the big sort of trapezoidal sidewalls are 1/16 of an inch aluminum that will be laser cut, and then the long side panels with all of these L channels here are a separate piece of 1/4 inch that will just be laying there.
Yeah, as shown, I don't think anything in deposition requires bending or like.
Yeah.
Have you considered what material you use? Maybe not the 1-inch parts?
It's like 60-61
Yeah.
aluminum plate.
Right now, it's all considered a 60-61 aluminum. Alex?
What prevents the PVC tube from just rotating? Like,
From just like spinning?
It's basically confined by those side plates.
Yeah,
you
so-
can't really see it in here, but they do overlap. It's
So,
1/8 inch thick PVC pipe and the 1/4 inch plate. It does overlap. Like on the inside face, it's the plate and then the curved tube, and it's
Yeah.
flush on the inside. But the 1/4 inch plate extends past.
And
on the
additionally-
outside, so that's
Additionally, I think we have here, this curve down here is the PVC pipe slotting into,
oh, okay. So there's a little notch on the end.
there's a little notch on the end that we're going to cut into it to fit into the front plate, yes.
And that also provides some of that support on the
Yeah.
front and back end, and then in the middle. So like that's kind of how it's held up actually.
All right, Josh,
Have we considered having 2 motors?
for the deposition?
Yeah, if it's such a, if the motor doesn't work, that.
I mean, so we haven't considered, the motor that we are going to be using is definitely, can definitely do the job with a correct gear ratio. This is us with a 100-to-1 gear ratio, and then we actually geared it back up a little bit. So if we were just to run 1-to-1, it drops down, it goes up to 29 Newton meters of torque, which is almost certainly enough.
Yeah, that's insane amounts of torque.
Yeah. So I don't think a second motor is necessary.
And if it was, we would just get a bigger motor, really, for complexity's sake.
Rockwell?
There's like a little hole where like the regolith comes out.
Yes, on the back.
Would it be possible for like the regolith to get like stuck or compressed? Because there is like a piece of like, metal walking.
Oh, you mean like sort of against the edge of this? Technically?
I mean, it's
Maybe?
technically possible.
I
but,
don't.
like, with it all falling down from gravity, like at that end of the robot, it's mostly going to pile up towards the larger like front side of the robot end, because that's where we're actually putting it all into the system.
Yeah.
So it's kind of going to cave down and probably not reach all the way to the end of the auger system to start. So
Additionally, the auger will of course be continuously aggravating the system and stirring it up. So I can't see a way which like a significant enough amount of regolith would be pressed against the small space there that it would cause a problem. We can look. We can look into that further. I don't expect it to be a big issue. Mike.
So, 2 questions. How did you guys calculate what torque that you think you need for your system?
Huh?
How did you calculate the torque that you think you need for that?
for excavation,
Yeah. No, not excavation.
For deposition, for that torque, the motor, we just use the motor spec sheet. At nominal load, it.
No, I mean, how do you know what you need to make and do the system?
there was some conversions from like commercially available augers and like how much horsepower they take, and there was some conversion from horsepower to torque, and
systems,
but
very much so some number
yeah.
fudging.
Testing would be great.
Also, on
Yes.
actuation, in the past, we've had problems getting systems to go up and down without binding. They've gone from 3 points that need to be in line to 5 points, and now not even all on the same road. Are you concerned about that, or do you think that?
With the struck rods, I think the struck rods are fine because it's going to be machine plates and it will slot in pretty exactly. So those 3 are going to be like very precise. So I think that collapses back down to like 1 internal structure and the 2 sides. And with the 2 sides, I think, yeah, that's something we will have to like kind of test and like make sure is working properly. But like, I don't think it's inherently going to be a problem. It's just a matter of testing and making sure we have like motor power and stuff correct for those linear actuators so that they're synced up properly.
Brian?
The bottom left, yeah, that's the linear actuator. It goes just through that 1/4-inch blade and then a bolt, yeah. Yeah, the plate will be laser cut, and then the actual like part sticking through is just part of the linear actuator. But I don't think it will be a problem, but like with how well it's confined, like at the top it can rotate around that top point, but like the overall tolerance of like that offset is like less than like a 20th of an inch. So any shifting is like going to be pretty minimal, I believe. And also like with the weight pressing it all down on that plate, I don't think it should be shifting very much.
If we really want to, we can apply a standard fit to that to get it more precise as like a locating fit, but that's something to look at later.
Pushing down. It'll just be like basically filling the space between the bolt and the plate on that bottom side with like a washer or like some fitting around it. But also, as you can see here, it's like already the bolt is like pretty close to the plate in terms of like that sort of clearance. So I don't think like it will be able to come out very much.
No, the face is like this big. You might need some sort of
It might need to be a pin, but like there are a couple of different options for how we actually do that exactly. Some sort of pin, basically like a safety pin type thing could work even. Or like, what are the? It's like a pin where like we put another pin through it, whatever.
Yeah.
I don't know exactly.
I was thinking the same thing.
Yeah, something like that. Yeah,
Spring pin would be
exactly how it's done, like bolt or like specific specialized pin. I don't think it will be able to come out very much at all. Like overall, the tolerances and like clearances seem to be pretty well fit.
Obviously, you don't have room for bolt head.
Yeah.
You
Yeah,
don't have room for bolt head.
yeah, you definitely do have a full head there.
Yeah.
That looks like
Okay, we'll look into an actual pin for that.
from 1/4-inch.
Well,
Yeah.
if they want them to be 1/4 inch, that's the backbone of their system.
Yeah.
That's actually going to be
That's
a full
kind of
inch
set in
from
for it.
another
We'll look
machine.
at an actual pin then. That's probably a better idea anyway, to be honest. Yeah, Josh.
All right, can you go back to, I think, 1 slide back? One more. Maybe another. There we go. All right. So, are those rod clamps that the structural rods go through?
Yes.
Are they tapped as well, or are they just clamps?
They're just clamps.
Okay. Okay.
You don't really see it, but like, if you look here, like obviously this clamp goes down, so there is a hole around where it clamps in, and then screws like around that hole, just to reduce like
Yeah.
basically thickness of that part.
Yeah.
Is that bent?
Whatever one we use for the majority of like cutting out a blade.
Yeah, we're just like the. I don't know specifically. We could, yeah.
I think for this part, it's really just this face here that interfaces with the like structural plate. I think it's just that face that matters. All the ones around here are not like critical for being super flat because they're not like resting up against anything really flat. It's just this face. What? Yeah, it's just straight, mostly straight. But like the belt is able to kind of sway a little bit and like fall into like kind of fill any minor deviances, I guess. Also, there's going to be a whole like the 16th-inch straight plate is what's going to actually be like probably flexing more than the actual side quarters. If that makes sense. I don't know if that does make sense.
Mike?
Is your like wedge shape on that circle, is that weight saving or is that
Like this?
Yeah.
Yeah, it's really just like, I don't think we needed extra material there, but like, we'll also do, there's going to be a lot of optimizing a lot of these parts, because right now a lot of stuff is either over-designed or like not optimally designed. Like, there's definitely things we can do to really like fix a lot of the stuff.
Top right photo, are you guys mounting onto the side of the drivetrain?
Yeah, this, we've widened, hold on, I'm gonna go to overall system. Okay, I'm just, where's the TLA?
There.
Yeah. Yeah, here. This is just mounting directly to the inside of the frame.
That's what we were going to do last year for the front prop. I think Matthew pointed out it was a bad idea. It's better to be mounting on the top of the drivetrain side.
Okay.
In principle, it's a bad idea. You don't want to have bolts supporting all the fasteners. On the other hand, those are actually quarter-inch aluminum, and we're using steel bolts. That is so strong that you literally don't care that it's a stupid idea.
Also, how do you get a wrench? How does it spin the bolt?
Like inside. There's, you can kind of see a little bit of a slot there. Drivetrain's gonna like, there's a cutout. Yeah. There's some like access points on drivetrain, like the drivetrain.
You have a question?
If we like accidentally pick up the rocks, are you worried about them getting jammed against the straight plate? If you feel like if a rock gets top beat up, it will jam against the straight plate.
With the belt being able to sway and also there being some clearance between the sidewalls and the actual like buckets, I don't think it should be a problem, but that's definitely something we'll have to test and like account for as we know more.
I'm not sure if, for the auger, it shouldn't be, for auger it shouldn't be a big concern at all. Because I don't think there are any rocks that are some sort of like perfect size, especially the clearance that we've got. There's only like 26 thousandths of an inch between the auger and the PVC pipe. That's definitely not big enough for any sort of rock that would be a problem to get into. And the auger should be able to handle any rock that isn't like, you know, an actual like rock, which I don't think we're dealing with.
Yeah.
Have you considered making the control system able so that if there was any dirt to lay on it, it would slide on the auger?
dust doesn't like to slide unless it's like you make it slide.
Yeah, unless there's like pretty significant vibrations, which
If you just
that's a
like,
whole other problem.
through like testing, we have a little sample of the dust, and if you can like, you can rotate to almost like 60 degrees before it starts to just like naturally sliding.
Okay. Yeah. The reason why I bring that up is I would always consider potentially anybody because of that location. And obviously, once you're digging up the dirt, you're going to be moving all the way back. So you will have time in between where you potentially get a little bit more. I'm not sure if that's a big enough gain of that.
For more like dust preventative measures, like we could add like a sort of wall here between the like excavation and P&H, or like some sort of cover, like dust tolerant prevention type stuff.
A little bit of a funnel.
Yeah. Yeah, good point though, because like we don't know exactly how much this will like kick up dust right now, so we might need to have like extra like maybe attached to the top system where it like kind of prevents it from being flung too far. Some sort of additional, but that kind of depends on the actual digging mechanics and how it moves the dust around, how far it throws it. So yeah.
Yep. Anthony?
I mean, it's kind of related to that, but there's definitely, at least based off of what the CAD drawing looks like, of just like the regular just being like dumped on top of the P&H box.
Yeah, we can. We'll try to.
So
We will eventually have something that makes that not possible.
One thing to note is that when
It's just not made yet.
One thing to note is that when we're trenching, the scrape plate is further down, so
Yeah.
it really does. Right now, the scrape plate's like, I don't know, 5 or 6 inches.
Side view.
Do you have
Oh
side
yeah,
view?
we do. Literally right next.
Yeah, as you can see, when we're traversing, the scrape plate is way up high. When we're trenching, the scrape plate is really just barely over the lip of deposition, which should significantly reduce the chance of flinging, unless we're spinning the bucket elevator at super speeds, which like maybe.
Good.
yeah, okay. Then just related to that, I think it might be beneficial to have like some sort of like mechanical like funneling.
Yeah.
Yeah.
And if it's concerned about like, I feel like, I mean, I'm not a mechanical person, but I feel like that could be like something that could be hinged, right? Or like in like a stowed position or like lie flat, right? But then like in like a working position or like, mount or something, I don't know.
Yeah, we're definitely thinking about implementing some sort of guide so that there's something.
To better
It's like
control
it's a contiguous path, but that's how we create it. Yes.
Have you changed the way the excavation method is last time?
Like just mounting flat to the side versus like that middle bar. Yeah, it's on the sides now. It's not on the middle bar anymore, like at all. So yeah, there's some extra holes that I didn't remove. Sorry about that. So many PDM stuff and like.
I love Aris. It's really good.
Also, in general, for like all the questions being asked, if you can put this in the like question Q&A thing as well. Yeah. Anyone who's asked questions or has questions, make sure you put it in the actual like Discord like channel for the questions.
So that we remember.
Because great to have reminders. And there's a lot of things that need to be done. So yeah, good to keep track of.
Yep.
And yeah, okay, questions.
Just a quick clarification. So it starts in the center, and then when it traverses, it moves all the way up.
Yeah, at the very beginning of the match is on the left, and then it immediately goes to the center traversal. And that's literally just like the max like extension of that linear actuator. And then once we're in the mining zone, it'll be minimum extension. So it's like we can do current sensing to detect the limits. We'll never need to return to that middle position unless it's manual
could try to do the same solution
it
we did
be
last
able
year.
to-
It wasn't a great solution,
With
but
it
it
being
kind of worked.
up to 4 inches deep, I think that's significantly different mechanics from last year with depth mining. So I don't think that will be as big of a problem. Also, like the hex shaft for that bottom drum is like maybe at ground level at the deepest, pretty much. That's what it's at about right now. It could be slightly lower, but like it's not going to go much further into the ground than that. Definitely that like bottom plate, like horizontal plate, will not go into the ground. So we're not pressing with that. And also wall mining, like it's going to be kind of stirring up the dust. So hopefully those mechanics will be more ideal. But that's definitely something we need to test and like make sure it works properly. We just don't know the exact soil mechanics right now, and it's difficult to find accurate equations.
I think there was like a few changes that were made. Like one, you can just like make it kind of sharper at the end, so it's not like flat. So
Yeah.
like use this, but yeah, there's like small things like design changes that can be made.
Yeah.
So they don't
Yeah.
have to be, done like during maintenance.
Yeah. Tell me that rivet scrape wheel wasn't a great idea. Tell me that didn't work. It was fantastic.
I mean,
Yeah, it was fantastic.
We can have that again if we want, but like, I don't think it's necessary this year.
Are there any other questions? Yes.
This is, well, it's probably an ignorant question because I've never seen an auger work with like sand before, but like, since it's angled, since the auger is angled upwards and there's no top on the tube, what stops the sand from just being pulled up and then just kind of falling down with the top stuff on it?
This is
Gravity.
not steep enough of an angle.
Yeah. So yeah, this will work. So the auger has a fairly large pitch. It's like a 4-inch. It's a 4-inch pitch auger, which means that realistically speaking, the dust is, when the dust is being stirred, it behaves a lot more like a fluid than a solid. So as it's traveling up the auger, it is much more so like just falling back down and sort of just getting pushed up by the motion. That might technically, I don't know that isn't a possibility, but industry uses.
It should be fine.
Industry
Augers are
uses.
designed to move stuff
Yeah.
from like at an angle to a higher elevation.
Industry screw elevators are very commonly used in industry for this exact purpose, which is why we were able to find a plastic auger and why we're fairly certain this is a good design for deposition.
Yes.
Brian?
Yeah, so you said that this is a really small box in the and it's kind of
Yeah.
I was worried about the small bucket I assume that's not going to be
It won't be a perfect fit, but it'll be a
very close.
It'll be a pretty close fit.
A lot smaller than any gravel would be.
Yeah.
like assuming that worst case scenario there's like some
Assuming worst case scenario, the auger is made out of plastic and the PVC pipe is made out of PVC. So I think probably the PVC pipe. But I don't. I mean, I actually have no idea. The auger is made out of polyethylene. The auger is made out of polyethylene. Yeah,
It's all smooth on the
there
inside.
is per specs. There's like 26 thousandths clearance between the pipe and the auger, which should be small enough that there isn't any sort of. Yeah, it's a bit bigger than an RC9 fit. It should be small enough that there isn't any gravel. There isn't any gravel that can get stuck there.
I just don't know what it would get stuck
Yeah,
on.
and if there's
It's
any
all
gravel that
smooth.
would get big enough, hopefully that gravel would probably get carried along by the motion, or by the regolith motion. Oh, like on the front or?
On the back end.
Yeah, on the back end. Oh, like yeah, like this edge right there. Yeah. That I don't know what would happen. I don't think that's a big possibility. That the gravel would have to be a very specific size to get stuck in that manner, which I don't think is a big concern.
The big thing is it's not just like the
definitely, that's something that we'll need to evaluate in testing to see how big of a concern it is.
I honestly, if we run into that problem, we're in an amazing place for mining.
Yeah, the deposition, we've tried to sort of maximize the height because the deposition does slope upwards.
Basically, with like that sort of pyramid, it's a lot.
That's
Like,
a lot of.
frankly absurd.
I'm very happy if that's a problem.
Yeah.
Max.
So you mentioned that the tolerance between the auger and the actual PVC pipe is like 26 thousandths or something like that.
Yeah.
How you're putting the PVC pipe in and how you're putting the auger in, do you see potential issues with manufacturing tolerance or just the rigidity of the system itself that the auger might come in contact and interfere with the PVC pipe in a way that might cause the system to fail?
To fully fail, probably not. But, like,
All of
you could
the-
scrape against it a little bit, but like
It's fine. I think it's
that's a
mostly.
matter of just like don't screw everything down really tight until you're sure it's
Yeah. All of the parts that are interfacing with the auger and the PVC pipe are like laser cut, which are laser cut or water jet, or quarter inch thick. Might be so that might be downsized to 3/16 or 1/8 as necessary. But all those parts should be either laser cut or water jet, which should give us enough tolerances that will be okay.
I'm more concerned about the flex of the front and back plates that are where the compared to each other. Yeah, because if those are attached to, like that one's attached to an L channel, the other one's attached somewhere else. If those flex or if those are some way attached that makes the tolerance interfere with the tolerance.
I think it should be rigid enough, especially with the slots and like all the L channel connecting in it. I think it should be fine.
If we end up putting it together and that is a big problem, and is rubbing, one of the nice things is that it's a plastic auger, which means that we can just like file down the edge a little bit.
It's not ideal.
Not ideal, certainly, but it's an option that we have. I'm not so concerned about that I think we should like upsize the PVC pipe or something.
I think it's just a lot of this system, like quarter-inch plate is like very rigid, and
Yeah.
with it being machined out to like a pretty high precision accuracy, whatever, I think it should all just fit together and play pretty nice. But if it doesn't, we have some options to kind of mitigate that.
Yep. Matthew?
Yeah.
It's not gonna save enough weight.
I mean, you can say it anyway.
Yeah.
Yeah, it's just sort of is there some percentage in using much thinner L channels instead of just ours? But our system is already small and
Yeah.
like it's just not gonna save more than grams.
Yeah. Also, I think having the gusset plate in the middle, well, all the gusset plates can be optimized, like cut off, trim some.
We can
of
cut
it.
some corners, etc.
So those will be weight savings from what it is now, but also just like because we're supporting it in the middle kind of area already, that gusset plate kind of acts as that L channel reinforcement a little bit. Obviously not perfect, but like I think it should be fine for like strength and mass.
I'll go measure question very quick.
Yeah.
Okay, one more and then we're done.
Yeah.
Okay.
What's the deposition strategy? Because like if you are depositing kind of like maybe 3/4 away from the back, and then like you have a square that you're depositing into. Every time you deposit like in a place like a little bit like I guess in front of it, you're pushing the deposition like the hill that you or the berm you just made with like in front of the road.
That really depends on how precise our positioning is and like how well we can hone to like a specific position. But like really basically go where the back of the auger is in like the middle of the berm to start, and then like as we're doing that sort of zigzag mining cycle, just like we're inching over each time.
Yeah. I was also, if it ends up being a problem, we could also make the deposition cycle the deposition motion more, sort of like just a reverse trenching motion, where as we push it out, we slowly drive forward just a little bit to spread out, if that's a concern. I don't know if that is. I sort of doubt it, but.
So we want to maybe build like layers instead of like a hill in the area.
It'll probably be building a hill from one side and then
Yeah.
over. Just like the operations. That's probably what it will turn out to be. Just because like,
Yeah.
I mean, okay, if we're doing 5 cycles, I don't think it's going to build up enough in one place to be like detrimental necessarily.
Well, like
I think we'll have enough room.
I think we need to move on.
Yeah.
Say if it's a problem, it's a really good problem to have because it means we're mining a lot.
Yeah.
A lot of things.
The big thing is
We need to do traction.
we need to make our system very reliable.
We need to make it good.
So that software has time.
Drivetrain.
This is the mic? Yes. It's a nice mic.
No, but okay, we're gonna start.
Alright. So we're gonna first do data system requirements overview. Front of the mic. Basically the drive system. Just go over a couple important requirements of just the drive system being able to move with only one wheel per side, with decent traction, being able to climb over obstacles that aren't readily detectable, like hopefully pits, and then being able to operate for the full time, as well as fitting within the max envelope of space and being able to support the full system. So general design plan overview, so initially for drive, our plan, what we did with the gearboxes is combine the past 2 years, roughly, in the fact of we kept the chain drive from last year, but with the ability of us being able to have more wiggle room, we pulled the motors back out and went back to the 2-to-1 gearboxes from 2 years ago. With this, we also moved the encoders to the front gearboxes just to have less stuff going on in the back. And then wheels are the same. Then for the frame, we switched to box tubes and C channels, and there's a second tube in the center, as you can kind of see within the TLA for better structural support, and also just more for X-Step to put stuff on.
Okay, so to compare the masses, so some of the masses from last year is on the left, and then this year is on the right. There is a small decrease, but it can be noted that not all the things have been added in. So, like for example, the battery holder and or the skid plate and fasteners. So considering that, we're likely to be a little bit more weight, but this would make sense as the dimensions have increased, and also we're using box tubes instead of C-channel as well.
Okay, so frame. So this year, instead of C-channels, we are making it out of 2x2 box tubes. We have the 3 main box tubes, and then we have a front box tube. You will see on that front box tube that there is only a single L channel supporting it and random holes. Those will be changed since Excavation has changed their mounting. Then we have some just dimensions of it. From what I hear after I left last night, the width has been made slightly wider, or it looks like it's already adjusted.
It was pushed over by like 0.002 inches just to make tolerance. Kyle wasn't having fun with the Phoenix rocks, so we just changed the tiniest bit more.
Interior dimension inches rather than centimeters. It was a chain of 2,000.
It's basically just rounding.
Okay. So there's the dimensions. There are currently 4 total access holes. There will be 2 on each of the box tubes. So we have ones in the back, on the top, so we can get to the gearbox holes, and then there will be 2 on these sides towards the front, so we can get to also gearbox mounting holes, and then some interior mounting for the front box tube. And then hole clarification, right now we have, I think, all the holes that we're going to need for mounting. However, we will just need to get proper sizing and then types of holes for manufacturing.
And then just some general clearance estimates. We have our current top of the frame to the bottom of the drive not counting houses is about 22 centimeters to 8.8 inches. Then our ground clearance, which is measured from based off pictures from last year's competition runs of roughly how far the wheels got trenched into the ground. We eyeballed right around the top of the BPS front of the wheel to initially we just did the bottom of the chain guard because we were going off the drivetrain TLA rather than full TLA because XM was having problems. That ends up being measured out to just under 3 inches. Doing a bit of math and not fully from eyeballing the full TLA with them just XF out, it would probably go down by at most a centimeter, but that still puts us like a 6 centimeter clearance.
Okay, so gearboxes. So, as was mentioned, we were still deciding at our last design review whether we would go with the linear system like this or whether we would go with something similar to last year with bevel gears. And with the extra dimensions, we were able to decide that we can do the linear system. So this is the gearbox from 2 years ago, and this was basically our model that we used for our adaptation for this year. And you'll notice that the encoder is much larger and different encoder. So for our one, we moved it to the front gearbox. And part of the reason that was on this, like how it is here, was in 2021, 2022, we used 4 motors with 4 gearboxes. We're not doing that this year. We're just going to do 2 motors, 2 gearboxes, and then do a chain linkage system. So we're doing the same gear ratio, and to compensate with that, we're going to be using a different internal motor gear ratio, because we have 2 of those, and we're going to be stepping that up to the larger of the 2 to balance that out. You also notice that the spacers on there are all keyed, and that's something we changed for this year. So with all that, this is what our gearboxes are going to look like this year. Front and back gearboxes. We also changed the tube dimensions just to make it more consistent. So now instead of being 3.5 by 1.75, it's now going to be 3 by 2 box tube, 1/8 inch thick walls. You can see we have the sprocket in there, same gear ratio, and we got rid of the keyed spacers except for the one in the middle, as both the sprocket and spur gear are going to be on the same key.
Alright, so as for the DFMEA, a couple of the ones to consider are listed above. So firstly, the frame was seen to bend last year due to moments and the stresses. So to compensate for that, we are to look into the FEA analysis, and if applicable, we would buy thicker material. Any small pieces that are subject to high stresses or strain are to be used with steel, and then any bigger pieces are to be used out of 6061, and then pieces not really prone to stress or strain are to be used with 6063 for making the components lighter. And then another consideration was the wheels getting stuck as we are moving and mining at the same time. Currently, we don't have any precautions for this. This would be really evaluated from testing, as this would be a thing is more difficult to simulate online. And then lastly, the gears turning or grinding of any sort, and or sand getting into there or regolith. This is to be checked by using properly sealed components and using aluminum tape to properly seal that up. But yeah, so that's basically it for our DFMEA.
And then our priorities moving forward are finalizing just general locations, and access rules depending on design changes, what we see needs fit, conditions, rules, wiring, and also hypothetically looking into acquiring most materials and parts before winter break, just so we can start as soon as possible. Yeah.
Josh.
Can you go back to the picture of the pole frame?
This one?
Yeah.
Yeah.
Okay.
This
also this one?
No, the other one.
Alright.
Okay. That's sorry. I was just checking for making sure there's a way to get into the gearbox to like put a hand in, and it looks like there isn't. So.
Brian. No, same thing.
Can you go to the DFMEA slide? So on the first one, the potential effects of the robot collapsing the chain drive is not able to move. Why is that a cosmetic alteration if the robot can't move?
Yeah, that would likely be a 4 at least. I'm not sure. I think so.
We'll revise the DFMEAs after PDR running should have accurate. It might be one where like one was like more severe. So
My guess is it was done, and it was just like someone's like, oh, I should change that.
yeah.
I get the feeling that
I just asked that because I know it can be time consuming, so I was wondering.
Yeah.
Yeah, just wondering.
It takes a while. It's very loud. But it works.
Keep in mind, expectation from PDR is that we'll have the initial designs. Yes, we want you to think about designing for manufacturing, but that'll be the expectation for CEOs. We aren't quite there yet, but that'll be something we'll make sure we get there.
I know like this last system, this pocket, the back here, is that what is shifting it towards like the middle and like the train has some sort of like constraint? Like if you want to keep all four blocks and just shift it right a little bit more, just keep it essentially.
Yeah, that can always be adjusted. Yeah.
It's not like how much like the train has constraint to, so it adds more weight to the sprocket. So
The sprocket and chain setup is full directly from last year's. Josh?
Yeah, so kind of bouncing off that manufacturing thing, and that needs a slide if you don't have an answer. But and this is partly just my own ignorance. Is it possible to like use a water jet or laser cutter to cut all access holes and only the front face of the sea channel, the box tube? No. Yeah, that's what I thought. But if you go back to that slide, I believe you have, those access holes are only in one face. Oh, that's CNC.
Yeah.
Okay.
I think that's not a whole
Okay. Yeah. Yeah. Okay, that's fine then. I was just making sure that that operation was possible. So. No.
How do you get the chain on the sprocket of the box tube and also how do you catch the chain? Why is it
Could you repeat the last bit?
And how do you catch the chain?
So you see the little red thing sticking out? That's the chain tensioner. It's basically, it's got a small like divot in the middle that's gonna run along the chain. It works pretty well last year. There's some design changes that might need to be addressed with it. But with issues we had amongst Drivetrain of just getting CAD to work, we didn't have enough time to devote to that pre-PDR, so it's gonna be at least something to before CDR. And then for the chain, getting on, we would basically get it into the gearbox and put them in, and it's a little scuffed, but it works. Avery?
What's preventing the bearings from falling out right now? There is also an E-ring on the outside one, and then the wheels on the
by 1 p.m. is the goal. So start by 1:05. Thank you, guys.
First.
Am I?
Yes. Last slide. I guess we'll go quickly.
Okay. First thing I'm talking about is SLAM. So what we've done so far, evaluated a few SLAM algorithms, nerf SLAM and warp SLAM specifically. Decided probably against those. We found another possible option called Google Cartographer. We might look into that, maybe not. But otherwise, our type map is probably the best, we decided. And last bullet point is just saying when we're testing, we really want to test, or we're planning on testing our tab map parameters. Maybe if we can change those and get it more accurate. Hopefully that's something we can look into basically. For the controllers part, Model Predictive Controller Group has created their sort of baseline. You can see the GIF going. We're ready to start testing speed improvements, maybe some other improvements. And some people might start looking into other path following controllers, so Pure Pursuit, Dynamic Window, Stanley maybe. It depends on who wants to look into what, and we'll basically evaluate to see which one is the most accurate and then the fastest for computation. For other controllers, just learned about this recently, so deposition is probably going to be just constant speed until the load cell says it's empty, right? And for excavation, we're thinking we need to design a system for picking the trenches, sort of like lanes, something to control the wheel and bucket speed in conjunction with each other, and that'll create something that's effectively straight line slow driving, obviously well lined, and so we don't fall into a trench or anything like that. This is behavior. So obviously you saw the concept of operations by systems at the beginning. This is what we came up with on our own. Obviously, it's not as detailed. But yeah, the overall idea is after a manual release, you plan the mining area, go to the mining area. You can do excavation. Once you are done excavating, you go to the berm, plan in the berm area, go to the berm area, try to line and deposit. The sort of states on the side are what I'm calling failure states. So you can see like what happens if something fails. You do that, you go back. Right now we don't have the failure states for excavation or deposition just because we didn't have all the info, so we can add that later. But yeah, that's the overall behavior plan. It's pretty similar, I think, to what systems did. And then overall, oh yeah, first off was the we made the arenas in our simulation, so that'll be used for testing behavior in simulation, basically. And then the additions to this model, like I said earlier, we're going to need the excavation and deposition failure states. We need to add the transitions, so how the excavation mechanism will transition between storage traversal, etc. How to get to places, those are other transitions. And then the state that is excavation will need to be expanded. As you can see, picking the trenches and doing the excavation, going back, all that sort of detail, basically. And then for the last thing is testing. So this is a list of testing that I know I want to do, hopefully before like the end of this first semester, basically. So the first thing is efficacy of SLAM, how far away it can see, and then what kinds of objects it can see, how tall, like can it see rocks, can it see large, tall buckets, obviously the rocks is more preferable. And then once we've done that, test the driving autonomy, get the current state of how it functions. For example, how fast pathfinding works, how MPC responds to a path, and how our PID velocity controller will sort of adapt. And that happens like if we're stuck in sand and it doesn't go fast enough, basically. And that last bullet point is like if anyone can think of any other data that they want for undergoing testing, we can work that in also.
Alright, cool. So firmware's been working more with sensor interfacing, more specifically the UWE testing. So we had a very basic test rig, and we are thinking of making a more advanced test rig that will simulate the berm area instead. So so basically the actual size. We have some distance data collected, and I'll show that in the coming slides in a bit. And we also ran a sample trilateration and had a 3D graft. And then for the encoder test, we have a little assembled test rig right there, and then defined the pinouts for connection, and we will be starting testing that in next week, hopefully. Yeah, so here's just all the data graphed. So if you see here, so each row is a different sensor. And then each column is a different sensor, each row is a different decrease. So you can see if we increase or decrease, there tends to also increase. And then this is just a raw error values compared to the expected. Here are some of the spreads. We trilated distance value calculated from those sensors. We found it to be fairly more consistent at closer distances up there. And then for 4 meters, this was possibly linear, and also for the 3 meters. And as we get further away, the data tends to spread out in the wrong area, but it does happen at every distance. And then here's just a better image showing the spread overall in a 3D plan. As for safety constraints, we wanted to trip software breakers before PNH's breakers are tripped. So based on their breakers chosen, for the drive motors, we want to trip 50% of the breaker, so 2.5 amps or higher for more than about a second. We want to shut off and then restart. And then same thing for the X-step motors, except for this, we are giving it 80% because it's more common for them to go at higher currents while mining.
So for telemetry, basically we have there's open source like software that we can use that gives us a nice dashboard of everything, really clean, and basically allows anyone to like look at the kind of this dashboard and kind of see what's going on. So basically status of every sensor and also kind of a 2D grid and where the robot is in the grid. And it's called Foxglove, like that's like the tool. And we got like a subscription to allow us to kind of also store our data like on their online servers as well for analysis. So this can be useful for kind of like our kind of data collection analysis, and kind of making sure we have like a good understanding of what we're doing when we do kind of a lot of our testing with the robot next semester and also this semester. And also the kind of myself and Alex have been working on is kind of making sure the data pipeline is really, really good so that we can do experiments quickly, and also store a lot of the data, because we have cameras, we have all of our running at like 60 hertz, and we have depth, and we have RGB, we have all of our we have like point clouds and a lot of data that we'd want to collect through each test, and that can tend to be gigabytes of data per test, and having that going from first being able to collect that quickly, and be able to then take that off of the robot to then use for analysis. This whole kind of like pipeline we're kind of like working on to make sure that
kind of like when we're complete with this by like CDR, we should be able to really be able to iterate really quickly on every single test, and also combined with the kind of telemetry system that I mentioned with Foxglove. So yeah.
Questions?
For the telemetry, what exactly are you planning? So like what will operate the robot, right? Say autonomous mode or manual mode. What are we streaming through? Is it just current and encoder data? Are we getting any sort of life or configuration? What are we displaying on that GUI? What would be the box cells?
Yeah, so we have every single sensor, every single motor, and then we'd have basically like check, or like basically like a check or like an X, or like basically like red, green, like basically that shows like active data streaming or no, we do not have data streaming from like that. Basically, are we able to control the motor? Or are we able to get data from this sensor? So this will basically like give that kind of health check. Basically, there's like going to be like basically like a grid that has that information, and this is like also like customizable too. So unfortunately, I don't have a visual for you guys today. But by CDR, we should have that done. Yeah.
And then as far as like the point cloud and all that stuff, is that all being done locally on the robot and not streamed at all, or are we streaming them back to the laptop?
Yeah, so we have to be very careful with what we stream. So with what's useful for us and what is also low latency to send over the wire, so it doesn't impede any manual control if we ever need to, so we don't like slow down the system. That means no images, or potentially compressed images. We have tried this, and we can get like a really like low bit rate, or low size or low resolution image, and like compress as well, sent over, and that like can work. So those tests we have to like actually still like do a little bit more to know like if we can send images. But basically, like we would have the data saved, all of like the raw data like saved on the robot. We have like 2 terabytes now, or is it 1 terabyte? What is it?
1 or 2 terabytes.
1 or 2 terabytes, like fast read and write on the device itself. So we can store a lot of data, all that raw data on the robot. So it'll always be storing on the robot, but what we see or what we like on the computer will be kind of like a very much like compressed version of that, and just the essential information. Like, yeah.
You know the slide with the breakers. Did you talk to anybody about KH?
No.
That was. You should not be using the breakers as a guide for when you should trip. The breakers themselves have a variable tripping point based off of like curves that depend on the amount of current you're shoving through it and temperature. So breakers are sized specifically, like the 5 amp breaker will not trip at 5 amps. Right? If you are tripping at 2.5 amps, you will trip almost immediately because nominally each of the drive motors pull 2.5 amps.
Okay. We'll adjust that. Yeah.
I can go over this with you guys at a later point, but yeah, those numbers need to be revised.
Yeah. Okay.
Those numbers were developed last night where it was Kevin and I talking. I didn't fully understand how the breakers works. I don't think Kevin fully understood how the breakers work. He knew that we needed to talk to someone from KH to firmly establish those numbers.
Yeah, we'll revise it later.
For like, so model predictive control, as I've said, is the path following, right?
Yeah.
So and that's we're using the same algorithm we did last year, or is that the decision based on like the guesses of
We're still gonna
evaluations?
As far as we've gotten in terms of that specifically, is that as a new member project, like new members have like finished creating that. The next thing we're gonna do is test that speed and then maybe see about different options.
Alright. So do we expect a similar speed of last year, or is there any work that's being done currently to improve that, or is that just the trace size between the different algorithms?
MPC is not the speed of our tab map. It's kind of the other way. Like how fast our tab map is able to update affects how accurate our driving will be, kind of essentially.
Is that the limiting factor affecting navigation?
I would say kind of, yeah, because our tab map is really slow right now. And it would be true of many, like any SLAM algorithm, I think.
So there's a few ways, like, so one of the things that actually there was like a member that was looking into this, but a few members, but like you can add a Cayman filter at the output of our odometry. Odometry is basically estimation of our current position, like relative, like differential, yeah. So the a Cayman filter you stick that in the output, you could basically have the output of the Cayman filter be like kind of like upsampled a lot, so you can run it at a lot higher speed. So right now it's around like 10 hertz. And we would want it to be above 20, because you're rate limited by how fast your position output is. That's like that's if you can't have your control running faster than your sensor input. So because of that, like we were running like MPC, since like output of our position was at 10 hertz, the MPC was running much slower at like 2 to 5. So that which rate limits how fast that we can move without hitting a rock. So we would want to basically bump up by an order of magnitude, and 10 to 15 hertz is like a good, I think, sweet spot for MPC. I think to be like fairly reactive enough to move at like between like 0.25 kind of like meters per second to kind of like 0.5 meters per second, around that speed. Because I remember like that kind of shot that we did was like maybe like I set the max to like 70%, so maybe like I think like half a meter per second or something, like maybe something like that. Yeah. So like maybe yeah, like around 0.2 to like 0.3 meters per second, like because you put down like in like the initial slide like 8 centimeters per second. What was calculated from?
That calculation is basically from the Alabama arena, right?
Yeah.
Us starting to us like him starting, right?
Yeah.
To us getting to the excavation arena, that's a known distance. How long does it take, like in manual control, when you were just like driving around the rocks? If we just assume that to be a linear distance, right? Because that's what we don't know our exact path.
Yeah.
That's at 8 centimeters per second. So
That was
it took
8
about 60 seconds to get that, like 2 meters. So then, I don't know if that math's right, but that is actually how fast we were going on manual.
And manual control.
So that 8 centimeters per second is actually like as an average speed over any path. It's probably not too far off. That was average over multiple competition paths.
Okay.
That 0.2 meters per second is very fast.
Okay.
And with 8 centimeters per second, we're looking at like 2 minutes to get from starting to excavation zone, and then traveling between excavation zone to deposition zone, we're looking at like 40 seconds, which I think are all like reasonable numbers.
40 seconds.
But that isn't including that time to like adjust orientation, all that stuff. That's just an average, speed.
Right. Okay. So I think
That adds time. We should be traveling minimally faster, but we're adding time by having to like adjust orientation.
And I think there will be like more obstacles to move around, as you mentioned, in this next competition. So I think I'll probably like revise that like statement and probably say like once we do testing like with like in the pit, like we can kind of have like a better estimate of like that top speed, kind of like that we're moving at like while like moving around obstacles. So yeah. So now that at least like we have a lot of the data collection stuff set up, we can now do that testing a little bit easier.
As it stands right now, we would expect, if we were to test the robot, right now it would be exactly as we saw in competition, right?
Yeah.
Like 2 to 3 seconds before we got an update on the map.
Yeah. Another thing is like but like the update on the map is like since the obstacles are the same, they're not moving obstacles, like that does reduce the like requirement of the speed of the map update.
Yeah, but if I remember correctly, we weren't adjusting trajectory until the map updated every time. We were doing that all at the same. We were updating the map, updating trajectory,
Yeah, so like the map is separate from the position of the robot in the map. So the we weren't necessarily waiting for like a new like map update. Like we wait for a new map update to complete planning. Like so we need a map to plan, and it'll internally will store like a map. And given a new map update, it'll like replan, right? Like so what I'm saying is. Like that doesn't determine the speed at which we move at, but that just is the speed at which we update our map. I mean, update our new path to follow. So the actual MPC, like how how MPC closed the loop. There's the only kind of inputs that rate limit it is how fast we get a odometry update, which I mentioned was like 10 hertz from like our kind of RTAB map. And then, like, if we're already following like a path, like that's the only input that, like the control. And then we're also slowed down by the, like, just the complexity of the MPC algorithm, so making it faster. So there's like parallelization and like a lot of other things that we can add to that. So we'll wanted to clear that. Yeah. Yeah. Cool.
Yeah, I'm looking at the requirements for software. One of them that you guys have had down was that we'd be able to push the boulders in the excavation zone to the side of the arena. Is that something that is currently in the control logic or plan to be, or what's the situation with that being pushed?
Pushing rocks around.
I had a plan for that.
You have a plan for that?
Is it?
I was just assuming we're gonna avoid rocks.
Okay, it's just avoiding. So no plans to, in the excavation zone, move obstacles aside?
Mechanically, is it designed to do that?
That's the other question I was gonna ask. I don't know if we're.
That would be less like.
That's what I thought.
I wonder where that was in there.
Power capacity has been powerful enough that we probably could push rocks around, but we also probably don't want to.
We would back up.
Yeah. Cool. So.
Looking at your behavior flow chart, it looks like the two different, like, you have failures in driving. You both have, oh wait, that says straight. I misread that as forward. I would assume that in this situation, it's for the two different driving failures. I would imagine that you basically are slinging the road backwards rather than continuing down whatever path you have, like go forwards versus backwards. This question is because I misread this initially, it just says straight. That I would imagine that you're going to have the robot go backwards in order to unseat itself from.
Yeah, the intuition for that was just the one run of manual control we got to do this year. And where it got stuck, I found the best way to get it out of stuck was go right on the back. So yeah.
Since you like another thing is like the controllers that we are you assuming that would be a manual control, like a correction?
No,
okay.
This is like the behavior cycle for
okay
automation.
for the autonomy. Okay, because like because since we have closed loop velocity, like meaning that we want to be having the wheel go a certain velocity, and if it's not, that means it's stuck. Then the control like feedback is to like increase power.
Yeah.
So like it should like yeah I think we can see we have to kind of do some more testing with the drivetrain. We haven't had time to really test the dynamics of the kind of like the drivetrain and the wheel, and I think that will also be changing slightly since we're turning into kind of a square instead of like a rectangle, so we'll be able to like rotate a lot easier like from like a drivetrain perspective. So that will be something we'll also have to update our simulation for as well.
This is kind of a question back at you, Alex. We kind of talked about sizing, Kevin. So initially when we stopped the robot, right, established
So if I understand your question, like it's basically like how are we getting the, so given we have like the 2D position like in the map, like where, so from my understanding, I believe like since I'll have to like get back to you on that. I think like I think specifically I was thinking that like since we know it'll be in like one corner, it's not symmetrical. So given that we know like the distance, like you have like two solutions. Like it can either be like if you know like the 2D position x and y from trilateration of where the bin is, you should be able to know like you should be able to at least like update the like there's that kind of like 2D transformation of where the bin is in the map relative to the current position. I don't see that we need to know the exact orientation of the robot, if that makes sense. Like I don't see like where that's necessary.
Because if the vertical say is off by 20 centimeters forward, let's talk more about this.
Yeah.
Maybe.
Yeah.
Okay, yeah.
We just represent all the PhDs.
I believe it's gonna be me and then you three, but I forget what order. So. Okay, we'll just figure it out. I went to like the deep rock too. There's a very deep rock galactic at the end. We can't have anything fun. They're deleting my What? That was the best one. It's part of the picture. Yeah. Are we good? All right, everybody. So welcome to P&H's part of PDR. Thank you all for coming. So first, just to remind everybody of the system architecture that we presented at SDR. I know that was a while ago, and some of you guys weren't here. So we have our input power going to the required power meter by NASA. Then we're planning on having a battery protection circuit designed by somebody that's doing senior design. So we actually won't be presenting on that today, but we're planning to have it. Then that'll go to our main fuse, which is designed to protect from battery shorts. And then that will go into the relay, which is triggered by the e-stop, which is required by NASA as well. Then that will split off into two different paths. One going to a 5-volt converter that will power our main microprocessor, the Jetson Nano, which will then go to a microcontroller that we're using as an I/O extender that will connect to all of the sensors. And on the other side, we'll have a little power distribution board that will have a secondary relay controlled by software to enable them to have a hardware shutoff for just the motors. That'll go to breakers for safety, motor controllers, current feedback, and then finally to the motors. So before we jump into the specifics of the design, I just want to go over some of the key aspects of the DFMEA really quickly. So you can see on all of these, there is a row for connection failure. So if something just isn't connected or is connected wrong, that definitely has the potential to damage components. Thankfully, this hopefully isn't something that we should have to worry about tremendously during the run, unless like vibrations are like off the charts. But what this means is that we have to do our due diligence while we're connecting the box and testing everything before we actually get it into a final state so that we don't fry anything, right? Because if you connect some things wrong, you could pretty easily fry some of these components. So for the motor controllers, the main failure mode for that would be overcurrent at the input. And so our main mitigation for that is the breakers that are designed to trip at stall, as well as the safety provided by the manual shut-off that software can provide. For the battery itself, there's a potential for that to short circuit if things are like connected wrong, or even just something happens. You never know what could happen. And so the main fuse is designed to protect from that as well. And then the over discharge of the battery could lead to damage to the battery capacity as we recharge it, which would overall decrease the cap of our total power, which might mess up some of our calculations. And theoretically, that will be cut off by the undervoltage protection circuit. We also have the buck converters that are converting from 24 to 5 volts. If those fail, then you can say goodbye to our microprocessor and all the sensors and stuff like that. And so there's not a great way to prevent those from failing entirely, but luckily there's not like a ton of failure modes. The only way that you're going to get a ton of current draw at the other end of that, if something's like directly shorted, which would again be a connection issue. And then for the teensy as well, same type of deal. There's no really way like during the run to prevent that, because most of the failure modes will come from assembly. So moving into the specifics of our design, we are moving to a larger capacity battery. Last year we used about 130 watt hour battery. This year we're moving up to 222 watt hour battery, which should be plenty to cover the expected power consumption over the course of the run. I think it's like it's at least double the amount that we theoretically would be drawing, right? We're also opting to move from a 7S battery to a 6S battery, which is lowering the voltage a little bit. So some of the stuff's going to be actually undervolted. But the reason that we did that was because we had an issue with our motor controllers last year that there was a 28 volt high limit, and so we would actually have to discharge the battery a little bit before we could actually run the robot, and so we just opted to undervolt the system a little bit, which does drop the efficiency, but theoretically the capacity is large enough to accommodate for that. It's also a similar cost to previous batteries. I believe it's about like 150. And then we have our box I/O.
So for box I/O, we have some new cable glands to house the power and the ground for all the motors. They are much easier to install than previous bulkhead designs, and they are also less likely to fail. For the actual connections to the box, we're using D-sub connectors, which are easier to solder. They can be placed pretty much, we can place the board pretty much anywhere in the e-box. And the D-sub connectors themselves have 44 pins, 18 of which are needed, which gives us some leeway in terms of the dimensions, with about a quarter of an inch on each side, right? Quarter of an inch, or is it half an inch?
Yeah, the connector itself is about 2 inches, which leave about like 0.2 inches on either side of the D-sub connector.
Right, yeah.
Cool. So motor controllers. Plan this year is to reuse the same motor controllers from last year because we have them and they're rather expensive. We also, when we did inventory earlier this fall, we found that we have 6 other saber-tooth controllers. They're the exact same. They're just in the BIDC. So we still need to test them to make sure that they're actually working. But this means that we have all the motor controllers we need, plus additional extras if we fry a few. So hopefully no new ones will need to be purchased. If we do happen to fry more than 6 motor controllers, that backups will be more saber-tooth controllers. They're about the similar cost, the saber-tooth dual channel 25 amp controllers, but they're drop-in replacement so so that they use the same communication protocol as the others. So there's nothing we need to change. We just need to replace the actual motor controller.
So for our circuit breakers, we decided to go with two separate breakers per motor, obviously. For the first one, they're both auto reset, and the first one is going to be 25 amps, and that's going to be for X-step. So we chose this based on one motor stalling, and if one motor were to stall, that'd have an output of approximately 41 amps, and it would break in 10 to 1,000 seconds. For the second one, that's going to be the Drivetrain reset breaker, and it's auto reset as well, and with one motor stalling, it's going to have an output of 11 amps, and it's going to break in approximately 6 to 60 seconds. The reason the range is so big is because it's based off temperature. So the graph is, it's a big curve, and it has a big space between each of the temperatures. So it's very unlikely for it to actually take 1,000 seconds. So yeah, those are the breakers.
Yeah, and then to elaborate that a little bit, just like how the system is, I guess, put together, we're planning on having 3 motor controllers. 2 of them will each have the Excavation-Deposition, they're using the same motor. So it's one of those motors and then an actuator. And then the third motor controller will have both of the drive motors on it. And so that 25 amp auto reset breaker is going to be for the motor controllers that have the X-step motor and an actuator, and the 5 amp one will be for the motor controller that has both drive motors. So then that's moving into the other safety components, being our fuse and relay. We're getting a new relay this year, rated for a little bit higher, 100 amps. It's also a little bit easier to connect to, since this is going to be mounted onto the power distribution PCB. And then to protect that relay, we're using a 60 amp main fuse. And so ideally at 100 amps, it'll trip at like a few seconds. You can see that this chart here, that the way that these work is that if it's a 60 amp fuse and you're putting 60 amps through it, so 100% of the rating, it won't trip, right? And 60 amps is really high for our system anyways. So theoretically, this thing should only blow if like the battery gets shorted or something, right? And that's to protect our relay from like welding itself shut, basically. So there's that. So now moving into some of the custom circuitry that we're doing. This is the power distribution board. I probably should have put a 3D layout on here now that I think about it. But the blue side on the left is the back side, and the right is the red is the front side. And so you can see that this is the footprint for the relay, and so you have the power input basically coming straight from let's see, I think it comes straight from like the main relay into this here, I think. But it goes from the relay into the 3 different breakers for the 3 different motor controllers, and then we have this circuitry here where we'll just put basically just a wire from the teensy, just soldering straight onto here, and all software is going to need to do is I think just deassert or assert that signal, and it'll shut this relay on or off. And then as far as temperature goes, it is always concerning when you're putting more than like 5 or so amps through like a PCB. And so the general protocol is to use planes, right? Everywhere you see this red, so this is a ground plane, and so that's like the negative return path, and then the red is all power, and so the active path there. And you can see that for a current of like 50 amps, to have a maximum temperature rise of like 10 degrees C, which is pretty standard, you require like a 86.2 millimeter trace. And as you can see, we're pretty much there. The entire width of this, I forgot to mention, is like 135 millimeters by like 92 millimeters, about. So that's like 5.3 by like 3.6 inches. And so the power planes here
are wide enough that we shouldn't see a significant temperature rise because of how much current we're shoving through this board. And again, 50 is a top level estimate. Like 50 is a current where we're like tripping breakers and stuff. So, and then cost estimate is going to be around like 25 for like 5 boards ish to get fabricated.
This is the current model for the current sensing PCB. It's the holes in the middle are what the motors will attach to, and that'll be where the current goes in. On the right, you can see last year's PCBs that we bought from a supplier, and the plan is to basically take the chip from that and integrate it onto our own PCB, so you can see the 6 footprints in the middle there where that chip will go. They'll have 30 amp, 31 amp capability to measure the full range of the motor, and the 2 chips on the right, you can see the ADC's 16-bit resolution as requested by, I'm pretty sure that's the one requested by software, but they have the capability that software needs. And the whole thing with all the components together is about $16, and the PCBs should add like about 7 to that, so that should be the total price. And you can see the connector there in white. That'll be where the TNC connects through I2C to communicate the data from both ADCs, and they'll be individually addressed, so software can pull data from either one. It's the overall schematic and PCB layout. It's mostly for keeping track of like the names of the chips. So I got the ACS 711, that's the Hall effect current sensor, and then on the right is the ADS 813, I think, for the ADC.
So this is our general block diagram for the TNC. We're currently in the process of making this schematic and just figuring out the connections and stuff. So if you want to go over a little about our pinout and what we have on there.
Yeah, so for our printout, we have 6 encoders. They're all named and listed there. They only need digital pins, so it's pretty easy to find spots for them since everything on the TNC board has a digital input option. And so you'll need a total of 12 pins for all of your encoders. And then moving on, we had 2 weight sensors. They need a clock signal and they need a data transfer signal, which fortunately there were only 2 of those on the board, and we had 2 weight sensors, so there were only 2 spots this could go, and those were filled up. For the motor controllers, just like last year, they're going to be daisy chained again, so they will need 1 RX and 1 TX, so just using the exact same from last year. For our current sensor board, I2C, same from last year again, and then lastly, our ultra wideband, also the same from last year, same pins.
Yeah, and just like going a little bit more into that, so our encoders output 4 signals, just A, B, and then their complementary signals, A naught, B naught. So we're planning to send those signals through RS422 like protocol receivers because they're differential, and just gonna send them through the receivers and then connect them directly to the breakout board. Other than that, we have to step down the motor encoders, probably gonna use voltage dividers to do that. Yeah, so I think that's pretty much it.
So I've still been working on the custom motor controller. That's been a ongoing project. Not a whole lot has changed since the previous design review for it, so all the specifications for that are pretty much the same. Yeah.
And that's it for us. Any questions?
So the saber tubes, I believe we have, I think 4 or 5 on the robot. Like, and we don't have any extra of the 2x25s that you guys said that you guys were using.
The ones that we have extra aren't the exact same model. They're saber tubes, but I'm not sure what model they are. We need to like test them for sure. Yeah.
And they're also a lot bigger.
Yeah.
And was that like taking into consideration that like is like the box size not a problem anymore in terms of the bigger ones that we have?
I don't know how tall they are, but we should have enough space like in the box, like square, like surface area wise.
Because like height wise,
Okay.
like quite maybe 2 inches or so.
We can take a look into that. Like honestly, my plan was to most likely, like I kind of anticipated the
the ones that we kind of had in stock. Like we still need to test them, but my plan was that they wouldn't like all work at least, and so my plan was to at least buy a couple of backups for sure.
And another quick kind of follow-up is like the breakers, like the auto reset, like, so is it like, so when like a stalling situation occurs, they're all like rated to, like, are there, do you have like breakers on each motor, right?
So it's going to be one breaker per motor controller, and you know there's pros and cons to doing it each way, but I think theoretically it still works to do it per motor controller instead of per motor. Yeah, was that your question?
Yeah, and then like and then after that, like following up, like the like when it does like stall, like basically 6 seconds, is that enough to damage the motor? Is that like because I remember like when we like did like our autonomous excavation test, like basic controller would kind of wait until it reaches like.
So theoretically, it's extremely difficult. Like even if we did have like a breaker that was, you know, per motor directly connected to the motor, it would be really difficult. Like the breakers aren't precise enough. They aren't as precise as like a software solution. Like it's not like this. It's analog circuitry, right? It's like I actually don't know exactly what the internal is like, but it's not like, you know, digital logic where it's like, oh, this is the current here. I need to trip myself, right? It probably depends on per motor controller, like the tripping time. It depends on like the temperature, right, that it's in, right? And so like there's a lot of different factors that determine the tripping time, and so you're not going to be able to get like a per second precise time. And the issue is if we size these any lower, right? Because theoretically, like that would be fixed by like, oh, you just size the breakers really low, and then you guarantee that if you stall, you trip in a few seconds, like guaranteed, right? The issue there is that then you risk tripping the breakers when you're running nominally. And so I guess like the happy medium here is to have them stall or have them trip in hopefully a reasonable amount of seconds, such that if the software, it's like a second fail-safe, right? Like kind of behind like the software switch.
And then, I think it's just, then we just have to make sure that we're aligned with
right.
the software.
Yeah, and then this is something, like especially because they're auto reset, it's a bit more difficult to test the fuse, but especially because they're auto reset, like I would like to get some like physical data of tripping times and things like that, just so we're not like estimating as much. That's definitely on the to-do list. Next.
Yeah. With the this is about the P&H box location. Now that it's I guess flags in on top of the deposition system, do you have any concerns at all about the wiring with it being in a new location? Any concerns of just wiring to motors that are currently there running or anything like that?
I mean, wire is pretty flexible, right? Like, and the motors are not in like crazy inaccessible places. So there's fundamentally like there's ways to get wire to the motor. Right. I guess the only concern would be I would need to look at the CAD again, but like there will need to be some length of.
Can you pull it up on the computer?
Oh, I guess it is just in the same presentation.
Escape that in.
I don't know where it is.
All the way
to the top. Oh, all the way to the top. Okay. Yeah. So, yeah, I mean, it doesn't really look like a terrible concern. My only, like, I guess concern would be, like, if the wires, because the wires need to extend straight for, like, at least a little bit before they curve. They can't curve at a 90-degree angle, right? And so I don't know if the specs are tight enough such that that period of length where it needs to be straight would like extend over the length of the robot. They don't. They don't. But overall, it should be fine. Yeah. Other questions?
With the deposition using a different motor from last year, does that seriously impact your plans at all?
What do you mean?
Last year the deposition motor used the motor that was used for actuation last year. Or last year deposition used the motor. This year we are using the motor that was used for actuation last year instead of that motor. It's the same voltage. I don't know if that messes with.
Deposition is the same motor as excavation, right?
Yes.
Yeah, that's fine.
Yes.
Question on the brake. So for motor controller and the breakers, so for the drivetrain system, if one motor is stalling, the breakers would not trip, right? The size for both motors?
So we sized it for one motor stalling. Because if both motors are stalling, it just means the breaker trips even faster.
Okay.
Basically.
And it won't. You're able to do that without having to trip the nominal operator.
Theoretically, yeah. Which is like we need to test it, but theoretically, like they shouldn't trip during nominal operation and during one motor. Because the difference between nominal and stalling, it's like 300 or 400% difference, right? And so like nominal operation for drive is about, I think, like 4.4 amps, right? And like I said, when these breakers are sized, being a 5 amp breaker, it's designed to not trip if you're shoving 5 amps through it, right? And even if you're shoving like 6 amps through it, it won't trip for like 5 to 10 minutes probably, right? And that has to be like consistent. And so with one motor stalling, right, you have, I think the stall that we calculated was like 8.6 amps for a drive motor. You add like the 2.2-ish, it's about 11, right? And so the 5 amp breaker at 11 amps, so at around 200% rated, should trip in like 6 seconds to a minute, right? Probably closer to 6 seconds.
And given that, like you said, right, you probably have to size these so that they're going to not trip during nominal. So would you characterize the breakers as truly stall protection for the motors, or more just like short circuit protection? Because if it stalls for 10 seconds, you view as high risk of motor damage.
The breakers are still stall protection, but it's like a second layer of safety. You know what I mean? Because like stalling and burning out the motors is such a high risk that it's worth having multiple layers of safety on that, right? So if the current feedback fails, right? Then at least there's a chance that the motor won't like destroy itself.
One thing was, do you think it'd be worth to have like hardware solution integrated with like the current sensing, where like, there's a second question I had. Like one was the like a BMS. Do you have a plan for like maybe shutting off within a certain voltage or something, auto shut off like the system, or like have like some indication, like just software at least, like that the voltage is like something low voltage, so we can turn off the robot automatically rather than having to like look at the reading from the sensor or the display.
Well, theoretically, like I mentioned, it's not in this slide deck, but there's somebody working on their senior design project is basically a battery protection circuit. So theoretically, it'll do individual battery cell monitoring, and it will be a secondary trigger to the main relay when you get below a certain voltage. I believe for a 6S battery, it's about 18 volts. So that's how we plan to do it now. Do you have concerns with that?
Also, like, it would also be nice, like, if you can get, like, with these new batteries, like, what would be the safe voltage, like, know which is, like, the safe operating voltage to, just for software, so.
Yeah, for sure. Yeah, I mean, off the top of my head, it's going to be probably around, like, from, like, fully charged, it'll probably be around 24 volts, then fully discharged, it'll be around 18 volts. Yeah. All right, any others? Alright. If not, then thank you guys.
Good. Yeah. All right, everyone. Thank you for coming to our PDR. It was a lot of work. Do you still have you have a question now? Oh, okay, yeah. So, yeah, we finally made it through. So at this point in our engineering life cycle, we have passed PDR and we are on to CDR. And CDR is going to be Saturday, January 13th. That's when it's currently scheduled. And the location is currently to be determined, but hopefully will be here. Keep in mind that this is the weekend we get back after that first week. So at this, make sure that you're spending some time at least to get everything ready by then. It seems like a long time to get to January 13th, but keep in mind we have winter break in there, we have Thanksgiving, we have dead week and finals. So it's not as much work time as you would think there. The expectation for CDR, this CDR is Critical Design Review. We want to have our designs finalized, we want to be ready for manufacturing, and with schedules for manufacturing and testing our systems. For software, that's probably just testing, but everyone else, yes, manufacturing is included in there. So important deliverables for CDR. This can be found in the review tracker for CDR, but to highlight the ones that are new or interesting here is that the BOM, we will want a full engineering BOM for our assembly for our robots by CDR. The DFMEAs that we have currently, I'll have them revised to make sure that they're accurate, and we will want to have them updated after our design changes as well to make sure that if we have any high RPN failure modes that we have designed for them and mitigated those. There will be an integration analysis conducted by systems. This will be just a report to look at the risks of possible integration when we do manufacture and assemble. We will also need manufacturing schedules from all sub-teams, at least hardware sub-teams, so a timeline for when you'll be going into what facility to manufacture what components, and then a testing schedule. So after you've manufactured, whether you're going to be testing components from vendors to make sure that they're up to spec, or just your parts to make sure that they meet the requirements. We will want to see that as well to make sure that we can hit our deadline for proof of life. And last but not least, this is more for the mechanical sub-teams, but similar as last year, we will be using an approval system to check off our parts and make sure they're ready for assembly. This system is called Design for X, or DFX, and right now we are trying to get it implemented into Eris. If that doesn't happen, we'll have to fall back onto some checklist system with our Google Sheets. But right now, our checklists, there will be actual checklists for each of these categories, but the 5 categories we'll be looking at are design for manufacturing, and that will be responsible by the fabrication team. Design for assembly, integration, and repair, that is also fabrication. Design for system requirements, basically if you've met the system requirements, that'll be responsibility of systems. Design for revision, basically CAD and design standards, making sure that you're not placing random negative extrusions for holes. That'll be for our chief engineer. And design for testing and inspection, that'll also be fabrication. All right, yeah, thank you, Max. So that completes preliminary design review. If you do have any more questions or you don't feel like your question was fully answered, make sure to put your question in the Discord in the revision channel, and we'll probably continue the conversation there. We also tried to document most of your questions, and we will be, leads will be working with you guys to make sure we are addressing any sort of outstanding concerns from this review. For those of you who joined us who are not in Lunabotics, thanks for coming. Do you guys have any feedback for us? Please feel free to send it my way. We're always looking for feedback and critique of our current system. But other than that, yeah, thank you guys for all your hard work the last 4 weeks since systems design review. We're looking to get that design very close to finalized in the next couple weeks here as we move into our design review process, and CDR will be very close coming at the beginning of next semester. But other than that, we should be wrapped up and y'all are free to go.